We have the vector field, right? Here's the vector field, kind of ugly looking. All right, I think I'm ready. So this becomes integral from where to where? -1 to 1 of the field evaluated on the curve, which means I need to take my curve components, replace the x in my field with t, replace my y with 1 plus t squared into the field. Leave it as a vector, though, right? So this will become x, which is t, over this. So it's this squared plus this squared, square root. So t squared plus 1 plus t squared, square root. Well, I thought that was going to be kind of clean, but I guess not. And then the y, so I do 1 plus t squared over the same exact thing that I had over there, right? Any questions on that piece? This is the x, this is the y. Dot that with what? Dot that with 1, 2t dt? Yes?
Is that not supposed to be 1 plus t squared squared?
Yeah, I missed my square, didn't I? Yes. That's the y value is this, but then I've got to square it. Yes, it's on both of these. Thank you. All right, let's dot that out. I'm just having this really bad feeling that this is going to be horrible, but let's see what happens. Okay, this equals integral -1 to 1. All right, dot this 1 times the first piece. Okay, that's not so bad. T over the square root of t squared plus 1 plus t squared squared. But then plus, now this times this, which the 2t is like on top, so it just passes through and just becomes 2t plus 2t cubed over the same thing. All of this dt. How are you feeling about that integral? That doesn't seems a little ugly. Do we have anything going for us here?
Can't you combine them?
You can put them together. I agree with that. All right, let me see what that denominator is. What is t squared times 1 plus t squared squared? What is that? It's t squared plus 1 plus 2t squared plus t to the 4th. That's what that is, which is just t to the 4th plus 3t squared plus 1. We good with that? I mean, that's what it is, right? That's what it is? Okay, so this becomes integral -1 to 1. What does my numerator become? Because I can put those together, right? 2t cubed plus 3t over the square root of t to the 4th plus 3t squared plus 1 dt. U sub. It just so happens that they made this problem work for you. What's the u sub? U is the whole thing inside the radical, right? So let's do it. We're going to go ahead and work this all the way through. The derivative of that is 4t squared plus 6t. That's what I meant to say, sorry. dt. There we go. That's what it is, right? Do we have 4t cubed plus 6t? No. Almost, right? We have half of it. So we could see that if we factor 2 out on ours, we would have this. So this is where things are kind of weird. Like, I know that everyone learns substitution just a little bit different. So I never know when I do this, like, how many students are like, what the hell are you doing? That is not the way I learned it. And I'm not here to try and reinvent the wheel. If you know how to do this, good. I mean, you're supposed to. But this is the way I do it. This is the way I usually teach my students to do it. It's a mix and match game. We try and tweak the right-hand side to make it turn into the left-hand side. I mean, to make it match up there. So I will replace this entire thing with 1/2 du. And everything on the bottom under the root is going to get replaced with u. So this integral becomes a new integral. This whole top became 1/2 du, so I'm going to put that back here, du, and then 1/2, right? 1/2 out here instead. And I'm left with 1 over root u. That's just, that's just u to the negative half, so antiderivative, that's just square root of u. Even if you have to take this into account also. But hopefully you agree with that. That's what that is. And now I'm going to switch back to the variable that I was working with, which was t. So I know that this becomes square root of t to the 4th plus 3t squared plus 1, evaluated -1 and 1, like that. Plug in 1. What do you get? Root 5? Minus, plug in -1. Root 5. Zero. So what is the conclusion? Given any vector field over any curve, the work is always 0. No. No. That, again, it's just to make this problem work out pretty nice. If you were to change the curve again and only do like half the parabola, go from 0 to 1 instead, your answer would have been root 5. If you want to include more of the parabola, your answer is going to vary, right? I need to change those examples. I need to make them, I don't like the fact that they both turn out to be 0. I'm not happy about that. Any questions? Man, it's already 10 after. Now, just a little notation for you. There's an equivalent form of this line integral of the vector field. So this is the way that we say work, right? This is work, but if you see this, it is equivalent to this. So this is where we're saying, where are we going to see those come into play? Here it is. If your vector field has p, q, and r as its component functions, then if you take the line integral along C of the scalar function p with respect to x, so you're just looking at that one with respect to x, then add to that this one with respect to y, and then this one with respect to z, that is the same as doing this integral. So sometimes it might be a little easier for us to use the other version. All right, now this is a problem I took out of the book, and I know for those of you who've taken physics, you may have seen something like this, and there may possibly be an easier way to do it, but let's just stick with what we're doing in this class right now, okay? A 180-pound man is carrying a 20-pound tool bag, walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Note, work is measured in foot-pounds. Also, weight is a force. Okay, so your weight on a planet is a force. I hope you've learned that your mass is independent of... Okay, all right. So everyone okay with the idea that weight is force? All right. So here's the picture. Here's the silo, like my silo. There it is. It's a 90-foot silo. It's got a 20-foot radius. And this man is going to walk around, go up with his bag all the way to the top. How much work did he do? So if I know this is going to be a work problem, right? Then what are the things I need? Work is going to be equal to line integral over c of f dot dr, right? So I'm going to need to know what is the field, right? What is the vector field? And I'm going to need to know r, which is the path function. So what would you like to talk about first? Which one are you most comfortable with at this point? You want to do R? Okay. You got to draw me this thing, right? Let's see. 1, 2, 3. Like, oh man, that's terrible. Seemed like at the end things went bad. Well, whatever. Okay. I have my computer drawing. It's even better. All right. So the guy goes around 3 times and he gets up to the top, right? Can you draw me that thing? I can give you some hint. If you look at it this way, it's just what? A circle. And what's the radius of that circle? 20, right? How would you draw a radius 20 circle with some sort of vector function? If I just asked you to draw me a circle, radius 20, you would do what? 20 cosine t, 20 sine t. But that would draw me just a circle on a flat sheet of paper. I actually want it to come up, right? Okay? So I'm hearing t. I'm almost there with you. Okay? Almost. Here's the kind of catch to it. I'm going to put right here question mark for a second. Right? Let's think about this. This component of the vector function tells me how high I'm going to be, right? So if I put t there, as I don't know if this is going to work, what is my restriction on t? Well, if you're going to use t here, it's got to be 90, right? But there's a problem with that. You need to draw 3 complete circles. So that's going to be the thing that's going to control your t. How do you draw 3 complete circles? Because that's what it says. He goes around 3 complete revolutions, right? What does your angle have to vary between? Because look, you're using trig functions, cosine and sine. What are you going to do to get 3 full revolutions? 0 to 6 pi, right? That's what has to be here, the way it's written. So this cannot be t, or else you're going to be 6 pi high. 6 times pi is about... Yeah, it's not 90, is it? So that's not quite going to work. Understand? So, but you're on the right track. It's just it can't just be t. So what do y'all think? Think this through. At t equals 0, where do you need to be in terms of height off the ground? 0. And at t equals 6 pi, you need to be where? 90.
15 over pi t.
You already reduced, right?
90 over 6.
There you go. Okay, we'll start with that. You want this 90 over 6 pi t. Look at this. That's what's going to go here. Now let's talk about y. At t equals 0, where are you? 0. So you're 0 height, right? At t is 6 pi, where are you? They cancel and you get 90. And this is linear, which means that as you go around, you're going up at the same rate, right? It's a linear incline. Does that make sense? Yes, go ahead.
I just passed over my head. Where'd you get to 90?
Oh, the silo is 90 feet high.
Oh, that's right.
Yep. Make sense? You could almost do it this way. If you kind of uncoil that thing and straighten it out, you know, if you uncoil it and keep its angle, that's the blue thing, but straightened out. You know, this has to be 90, right? But the question is, how long is this?
It's 3 times the circumference.
Three times the circumference of one circle. What's the circumference of a circle? 2 pi times r is the circumference of a circle. R was, so 40 pi is the circumference, and then do what? Divide by? No. Multiply, divide? Is that going to work? No, that's not going to work. I'm trying to make a connection that would be easy. It's not going to work that way. Because you would need the actual arc length to get this side. Or I'm sorry, to get this distance. So let's not mess with that. That'll get uglier than it needs to be. I think just looking at this, most people can see the relationship. You need it to be linear because you're assuming the stairs are going up at the same rate the whole time, right? And you need it to be 90 at 6 pi and 0 at 0. So that'll work. All right, so far, is that all right?
Yeah.
Okay, now we'll need the derivative of this. Reduce the fraction, right? If you reduce, 6 goes into each of those. So 15 over pi t. Joel, is that the way you did it? How do you reason it the same sort of way?
Yeah.
Okay. All right, so we'll need the derivative in the integral, so I'm going to get it now. Derivative of this, negative 20 sine t. Derivative of that, 20 cosine t. Derivative of that is just 15 over pi. I need the field. What's the field? 0, 0, negative 180. Where are you getting that from? So the only thing we're assuming is acting on this guy is a gravitational force, right? But it's him in his bag. He had a 20-pound bag. 200, right? Yes? Negative. Okay, so negative 200 or positive 200? What do we want? Does it matter? It depends on what you're saying here. Do you want to know the work done by gravity, or do you want to know the work done by the man? You see what I'm saying? The force downward is gravity. He has to overcome that force going up, right? So he does work, right, which you could consider like positive work,